Hey everyone, and welcome back for another deep dive.
Yeah,
Sometimes it's the little things that make a big difference, right?
absolutely.
And that's exactly what we're diving into today. We're talking about reinforced composites, like adding those tiny particles or fibers to a material to totally transform its properties and give it almost like,
Superpowers.
yeah, superpower. So we've got a couple of presentations lined up all about 3D printing these super materials. So get ready to explore the microscopic world that's shaping the future of like everything.
It really is amazing how these microscopic additions, things
Mhm.
you can barely even see, can completely change how a material behaves,
Ah,
at a much larger scale.
yeah.
It's like taking ordinary plastic and turning it into something you'd find on a spaceship.
All right. So let's start with the basics here.
Yeah.
Particle reinforced composites. What are we even talking about here? Is this like mixing sand into concrete to make it stronger?
It's similar in concept, but we're talking about way tinier particles. Imagine you have a material like a basic plastic, and you sprinkle in a bunch of microscopic particles. These could be ceramic, metal, or even another type of polymer. Now, these particles, they act as tiny obstacles within the material. They make it much harder for the material to deform or break under stress.
So it's like adding a bunch of tiny speed bumps throughout the material. Okay, I get that. But what kind of particles are we talking about? And what superpowers do they give to the material?
That's where it gets really interesting. The type of particle you choose determines the specific properties that you enhance. For example, ceramics like silica and alumina are known for their strength and wear resistance. So you'll find these in things like engine parts or cutting tools because they can withstand a lot of friction and heat without wearing down.
So that means your engine lasts longer and your tools stay sharper. That's pretty practical. So ceramics are like the tough guys of the particle world. What about metal particles? I wouldn't think metal would make something tougher. Wouldn't it make it more bendy?
That's a good question. Metals actually bring a different kind of superpower to the table. Metal particles like aluminum or copper are fantastic for enhancing conductivity. So they're used in applications where you need to manage heat or electricity efficiently. Think about electronics or high-performance systems that generate a lot of heat. Metal particles help to dissipate that heat quickly and prevent damage.
So it's like adding tiny electrical pathways throughout the material. Okay, that's pretty cool. So we've got ceramics for strength metals, for conductivity. What about polymers?
Polymers are often added to improve tensile strength and impact resistance. They give the material a little bit more give, so it can absorb shocks and impacts without shattering. Think about things like protective gear sporting goods or even car bumpers. Polymer particles help these materials withstand those sudden forces and keep you safe.
Okay, so it's like adding a bit of a cushion or a shock absorber into the mix. All right, that makes sense. But how do we actually get these particles into the material, especially when we're talking about complex shapes and designs? This is where 3D printing comes in, right?
Exactly. 3D printing has revolutionized the way we create these composites. It gives us incredible control over where the particles go and how they're distributed within the material. One common technique is fused deposition modeling, or FDM.
FDM, that sounds familiar. Isn't that the kind of 3D printer a lot of people have at home these days?
Yes, it is. In FDM, you basically extrude a thermoplastic filament, like a thin string of plastic that's already loaded with these particles. It's like squeezing out toothpaste, but instead of toothpaste, you're building a three-dimensional object layer by layer with those particles already embedded in each layer.
So it's like a microscopic assembly line, building the material up with those superpowers baked right in. Are there other ways to 3D print these composites?
There are quite a few, actually. Another common method is powder bed fusion, or PBF. This technique uses lasers to fuse powdered material, including those reinforcing particles, layer by layer. It's like using a tiny laser beam to selectively melt the powder and build up the object in a very precise way.
Wow, sounds like laser surgery for materials. I'm guessing there are even more techniques out there.
You're right. There's direct energy deposition, or DD, which combines powder melting and deposition using lasers or electron beams. But here's where it gets really interesting. All these different techniques give us a level of control over particle placement that traditional manufacturing methods simply can't match.
So we're not just adding particles, we're strategically placing them exactly where they'll have the most impact. That's pretty powerful.
Hmm.
But with all this advanced technology, are there any downsides to 3D printing these composites? Are there any limitations we should be aware of?
That's a great question, and one that researchers are constantly working on. While 3D printing offers amazing potential, there are some challenges. One issue is achieving strong interlayer bonding, basically making sure those individual layers stick together really well. If the bond between layers isn't strong enough, the material can weaken or even delaminate under stress.
So it's like building a brick wall. If the mortar between the bricks isn't strong, the whole wall could crumble.
Okay.
What else?
Another challenge is warping or distortion that can occur during the printing process. This happens when different parts of the object cool down at different rates, leading to internal stresses that can warp the final shape.
Oh, so if I mess up the temperature even a little, the whole thing could warp. That's a little stressful. I'm guessing surface finish is also important, especially if we're talking about precise parts.
You're right, surface finish is another consideration. The size of the particles can actually influence the smoothness of the surface. Larger particles tend to create a rougher surface, which might not be ideal for applications where you need high precision or smooth aesthetics.
So even something as tiny as particle size can have a big impact on the final product. It's wild how these microscopic details have such huge consequences.
It is a great example of how material science is all about understanding those tiny details and how they influence the bigger picture.
Okay, before we move on, I just want to make sure I've got this straight. We've talked about how particle reinforced composites work and how 3D printing gives us amazing control over their creation. We've also covered some of the challenges like interlayer bonding, warping, and surface finish. What I'm really curious about now is how these composites are actually being used in the real world. Where are they making a difference?
That's a great segue into the next part of our deep dive. We're going to take a look at the amazing applications of these materials from aerospace to healthcare and beyond. Get ready because it's about to get even more exciting.
Okay, I'm ready. Let's do it.
So now let's move on to fiber reinforced composites. Instead of those tiny particles, we're talking about adding fibers. Think like tiny threads to give materials incredible strength and resilience.
Okay, fibers. So instead of speed bumps throughout the material, it's more like adding a bunch of tiny support beams. I'm guessing that makes a big difference, especially when it comes to things that need to be super strong, right?
Oh. Exactly. Fibers act like reinforcing rods within the material. They're incredibly good at resisting pulling and stretching forces. Think about an airplane wing, for example. It needs to be incredibly strong to withstand the forces of lift, but also lightweight to help the plane fly.
So fiber-reinforced composites are like the secret ingredient for making planes lighter and more fuel efficient. That's pretty cool. And I've heard that these composites are also used in things like bridges and buildings, right?
You're absolutely right. Those bridge cables that hold up massive amounts of weight, often they're made with fiber-reinforced composites because they offer that exceptional strength-to-weight ratio. You get the strength of steel, but with a fraction of the weight.
Okay, that's kind of mind-blowing. So we've got strength and lightness, but there must be other benefits too, right? Otherwise, why wouldn't we just use steel for everything?
Great point. One of the big advantages of fiber-reinforced composites is their thermal stability. They can handle high temperatures without warping or losing their strength. Think about engine components or heat shields. Those need to withstand extreme heat, and fiber-reinforced composites are up to the challenge.
So they're like the superheroes of the material world. Strong, lightweight, heat-resistant. What can't they do?
Well, they're not invincible, but they're pretty close. Another advantage is dimensional accuracy. Fibers help minimize shrinkage and warping during manufacturing, so the final parts retain their intended shape with incredible precision. This is crucial for things like aerospace components or medical implants where even tiny deviations can be a big problem.
They're precise too.
Yeah.
It's starting to sound like fiber-reinforced composites are the answer to everything. But before we get too carried away, let's talk about the fibers themselves. What kind of fibers are we actually talking about here?
There are a few superstars in the world of reinforcing fibers, each with its own set of unique properties. One you've probably heard of is carbon fiber. It's known for its extreme tensile strength and stiffness. It's incredibly lightweight, but incredibly strong, which is why you see it used in high-performance applications like airplanes, race cars, and even some really fancy bicycles.
Yeah, carbon fiber. That man's so high-tech and futuristic. What about other options? Are there any fibers that are, a little more down to earth?
Absolutely. Another popular choice is Kevlar. It's famous for its impact resistance and toughness. You'll find Kevlar in things like bulletproof vests, helmets, and other protective gear. Did you know Kevlar was originally invented to replace steel in racing tires?
Wow, I did not know that.
Yeah.
So carbon fiber for strength and lightness. Kevlar for when you need some serious impact protection. Are there any options for those of us who aren't building spaceships or stopping bullets?
Of course. Fiberglass is a more budget-friendly option that still offers good strength and thermal resistance. It's used in a ton of everyday applications like boat hulls, car bodies, and even insulation materials.
Okay, so there's a fiber for every need and budget. Now, I'm curious about how we actually get these fibers integrated into the material. Is 3D printing still the go-to method here?
Absolutely. 3D printing is revolutionizing how we create fiber-reinforced composites. It allows for incredible precision and control over where those fibers go and how they're oriented within the material.
And I'm guessing that fiber orientation is super important. Like if you want something to be strong in a particular direction, you need to align the fibers accordingly, right?
Exactly. It's like building a house. You wouldn't just throw the support beams in any random direction, right? You'd carefully position them to create the strongest structure possible. It's the same principle with fiber-reinforced composites.
Makes sense. So how does 3D printing give us that level of control? What kind of techniques are we talking about?
One popular technique is a variation of FDM called continuous fiber fabrication, or CFF. Instead of using a filament that's already loaded with fibers, CFF adds long, continuous fibers during the printing process.
Continuous fiber. So instead of little chopped up pieces, you're adding long, unbroken strands. That sounds like it makes for some seriously strong materials.
You got it. It creates a truly reinforced structure with exceptional load-bearing capabilities. And that's just one technique. There's also direct ink writing, or DIW, which uses a special type of ink that's loaded with short fibers. It allows you to create very complex geometries and even combine different materials like ceramics or metals for even more unique properties.
So it's like mixing and matching different ingredients to create the perfect recipe for strength and functionality. What about those powder-based and photopolymer 3D printing techniques we talked about earlier? Are those also used with fibers?
You bet. Techniques like selective laser sintering, or SLS, can be used to fuse powdered thermoplastic composites that contain fibers. This creates what we call isotropic parts, meaning they have uniform properties in all directions. And photopolymer techniques like SLA and DLP use liquid resins that are mixed with short fibers to create incredibly detailed parts with enhanced strength.
It's amazing how 3D printing offers so many different ways to work with fibers no matter what you're trying to create. But I imagine there are still some challenges and considerations when it comes to actually printing these materials, right?
You're right, it's not always a walk in the park. Just like with any 3D printing process, there are crucial parameters that need to be carefully controlled. Things like nozzle temperature, print speed, and even the orientation of the fibers all play a role in determining the quality and strength of the final product.
So it's not just about picking the right fibers, it's also about how you print them. Can you give us some examples of how those parameters affect the final product?
Sure. Nozzle temperature is crucial for making sure the fibers bond properly with the surrounding material. Think about it like gluing two pieces of wood together. If the glue isn't hot enough, it won't create a strong bond.
So if the nozzle temperature is off, even by a little bit, it could weaken the whole structure. That's a little nerve-wracking. What about print speed? How does that affect things?
Print speed is another important factor. Slower speeds generally give you better bonding between the layers. But of course, that also means longer print times. It's a trade-off between speed and quality, just like with any printing process.
Slower is usually better, but sometimes you need to get things done quickly. And what about the orientation of the fibers? We talked about how that's important, but can you give us some more specifics on how it affects the final product?
Absolutely. The way the fibers are laid down during printing, which we call the raster angle, has a huge impact on the strength of the composite in different directions. By optimizing that angle, you can make a part incredibly strong in the direction it needs to be, while maybe being more flexible in other areas.
It's like those bridges again, where the beams are strategically placed to withstand the specific loads they'll experience. It's fascinating how those tiny fibers can be manipulated to create such strong and intricate structures.
It's a testament to the incredible advancements in 3D printing technology and the ingenuity of the engineers and scientists who are pushing the boundaries of what's possible.
But it's not just about the printing process itself. The materials themselves and how they interact are equally important, aren't they?
You're exactly right. Material selection and microstructure analysis are crucial for making sure everything works as intended. You need to choose the right matrix material, which is the material that surrounds the fibers. It's usually a thermoplastic like nylon, PLA, PEEK, or even epoxy.
So it's like choosing the right fabric to go with your thread. You want something that's compatible and will create a strong and durable final product. And what about microstructure analysis? What's that all about?
Microstructure analysis is like looking at the composite under a superpowered microscope. We use techniques like scanning electron microscopy, or SM, to examine the fiber orientation. Look for any tiny voids or imperfections and make sure the fibers are bonding properly with the surrounding material.
So it's like a quality control check to make sure all those microscopic details are in order, because if they're not, I imagine that could lead to some pretty big problems down the road, right?
Exactly. Poor bonding between the fiber and the matrix can significantly weaken the composite. It's like having a loose thread in a garment. It might seem small, but it can unravel the whole thing.
Wow, it's amazing how those microscopic details can have such a massive impact on the strength and performance of the material. It really is a case of the little things matter. But ultimately, it all comes down to how strong the final product is. How do we actually measure and test the strength of these 3D printed composites?
That's a great question, and one that takes us into the realm of mechanical testing and analysis. We use specialized equipment to apply controlled forces to the material and measure how it responds. This tells us things like tensile strength, compressive strength, flexural strength, and impact resistance.
So we're basically putting these materials through their paces to see how much they can handle before they break. That sounds intense. Can you give us some examples of how these tests are conducted?
Sure, one common test is the tensile test, where we pull on a sample of the material until it breaks. This tells us the maximum force it can withstand before it fails in tension.
It's like seeing how much weight you can lift at the gym, except in this case, it's the material that's doing the heavy lifting. What about other types of tests?
Another important test is the impact test, where we drop a weight onto a sample of the material to see how well it absorbs the impact. This is crucial for things like helmets and protective gear, where you want the material to absorb as much energy as possible to protect the wearer.
So it's like dropping your phone case from a height to see if it protects your phone. Except, of course, these tests are much more sophisticated and controlled. What about testing for things like stiffness and flexibility?
We have tests for those properties as well. The flexural test measures how much a material bends under load, while the compression test measures how well it resists being squeezed.
So we're basically getting a full picture of how the material behaves under all sorts of different forces and stresses. That's really impressive. But I'm guessing the results of these tests aren't just about getting a number. They actually inform the design process, don't they?
Absolutely. The data we get from these tests helps us understand the strengths and weaknesses of different materials and how they perform under real-world conditions. This information is then used to optimize the design of products and components to ensure they meet the specific requirements of their intended applications.
So it's like a feedback loop where the testing informs the design and the design informs the testing, ultimately leading to better and better products.
It's a great example of how science and engineering work hand in hand to create innovative solutions. And speaking of solutions, let's shift gears and explore some of the amazing real-world applications of these incredible materials. From airplanes to medical implants, fiber-reinforced composites are making a difference in a wide range of fields.
That sounds amazing. I'm really excited to learn more about how these materials are being used to improve our lives and push the boundaries of what's possible. So we've talked about all these amazing applications for reinforced composites in like aerospace and automotive and healthcare and even renewable energy. But I feel like we're just scratching the surface here. What does the future hold for these materials? What kind of mind-blowing advancements are on the horizon?
Well, the future of reinforced composites is looking incredibly bright. Researchers and engineers are pushing the boundaries in so many exciting directions.
Okay, spill the beans. What are you most excited about? What kind of sci-fi stuff are we talking about here?
One area that's generating a lot of buzz is self-healing composites. Imagine materials that can actually repair themselves when they're damaged.
Wait, self-healing materials? That sounds like something straight out of a superhero movie. How's that even possible?
Researchers are exploring a few different approaches, but one promising method involves embedding tiny capsules filled with a special healing agent within the material. When the material gets damaged, these capsules rupture and release the healing agent, which then reacts to seal up the damage.
So it's like the material has its own built-in first aid kit. That's incredible. What other futuristic advancements are in the works?
Another fascinating area of research is bio-inspired composites. Nature has been designing and optimizing materials for millions of years, so we're learning a lot from biological structures.
Bio-inspiration. That's so cool. What kind of natural structures are we talking about here?
Think about the incredible strength and flexibility of spider silk, or the lightweight yet sturdy structure of bird bones, or even the self-cleaning properties of a lotus leaf. Researchers are studying these natural wonders to develop composites that mimic those amazing properties.
So we're taking inspiration from nature to create the next generation of super materials. It's like Mother Nature is the ultimate engineer. Are there any other breakthroughs on the horizon that you're particularly excited about?
Definitely. The integration of artificial intelligence and machine learning into materials science is opening up some truly mind-blowing possibilities. Imagine algorithms that can predict the perfect combination of materials and processing parameters to create a composite with very specific properties.
So AI is going to be like our co-pilot in designing and creating these materials.
Exactly. AI can help us accelerate the discovery and development of new materials, optimize their performance, and even design structures that are perfectly tailored for specific applications.
It sounds like the future of reinforced composites is going to be shaped by a convergence of biology, technology, and human ingenuity. What an exciting time to be following this field.
I couldn't agree more. It's a field that's constantly evolving, and I can't wait to see what breakthroughs and innovations emerge in the years to come.
Well, I think it's safe to say that we've all gained a newfound appreciation for the incredible world of reinforced composites. From those tiny particles and fibers to the mind-boggling applications and the futuristic possibilities, it's been an amazing journey.
It's been a pleasure exploring this topic with you. And to our listeners, we encourage you to keep learning, stay curious, and who knows, maybe you will be the one to make the next big breakthrough in the world of material science.
Thanks for joining us on this deep dive into the fascinating world of reinforced composites. We'll see you next time as we continue to explore the cutting edge of science and technology.